Uh, our speaker today is Bo Guo. He's at the University of Arizona right now, a colleague of mine, and his domain expertise, his field is groundwater modeling. He's done a lot of work on PFAS and pollutant and so on. Very, very concerned about how we build models in order to help us solve problems. But one of the things about Bo that very much stuck with me was when he first came to the U of A to give his introductory, what do you call it, interview talk. He talked a lot about um, choosing the appropriate model and representation uh, to help solve different problems, different scales, and so on. So he was not one of these people who said there's, this fully distributed, highly detailed model is the model, and that's the only way to go. And Bo and I have lots of conversations offline at the U of A about these kinds of subjects. So with that, Bo, maybe you could just start with a little bit of background, where you got your degrees and everything, and what your broad interest is, and then we'll leave it entirely up to you.
Yeah. Well, first of all, thank you, Hoshin. Thank you, Lila, for the invitation. I actually have been aware of the information theory discussion group for a couple of years now, for a few years now from Hoshin. So I've heard a lot of good things about it. And it's really a great pleasure to meet the group and to share some of the work that we have been doing. So I grew up in China and did my undergrad in Tsinghua University in Beijing. And then I was 2011. I then came to the United States, did my PhD in Princeton with Maxilia in subsurface hydrology. And then after that, I moved to the West Coast and did a 2-year postdoc in Stanford, and then joined the University of Arizona Hydrology and Atmospheric Sciences Department. And I have been, so I'm a computational subsurface hydrologist. So I've, study basically what the bunch of stuff that flowing through porous materials. So the porous materials can be soil, can be different type of rocks, and also can be other type of industrial materials. But one of the primary applications of our work is to look at um, contaminant transport in soils and groundwater, and then also chemical weathering, landscape evolution was part of the Biosphere 2 landscape evolution observatory team. So that's sort of the themes that I expanded here after I moved to Tucson, working with colleagues here. So today, what I will talk about mainly is sort of an area that I started after I moved to Tucson, which is PFAS. So this is actually a talk that I gave a couple of weeks ago in Switzerland at our Gordon conference, Gordon Research Conference, um, that focuses on flow and transport in permeable media. So, I mean, I'm reusing this because this has sort of some background introduction about the problem, and then I can go into some of the formulations. And so, I think the connection of the work to information theory is that we're thinking about upscaling, right? So the talk that I presented was in the upscaling session. Upscaling is basically information compression, and it's basically very aligned with the information theory. You want to minimize the description, but then also maximize the description, but then also minimize the information loss while doing the upscaling process. And since we don't have a huge group, so I think I'm gonna go like pretty casual now. Just I can introduce the slides and the concepts, and you can feel free to interrupt me anytime. And it's more of a discussion, I think, which I would love, right? So because I don't know much about, I mean, I think the group, most of you do not focus on porous media physics, right? So if you have any questions, feel free to stop me, and I would be happy to do that. Okay. So you can see the title is like transport of surface active contaminants in unsaturated porous media across scales. I'll tell you that surface active contaminants, it's a more general thing, but in here in this talk is mostly PFAS, PFAS. I'll explain what they are later. And the focus is really on like interfaces and then thin water films covering soil grains, and how do we think about these detailed processes that turned out to be important, but then we cannot represent them explicitly at this tiny scale when we think about bigger scale problems like contaminated sites and stuff, right? So that's really the quest is to first understand the details and then think about how we can incorporate this in bigger scale models that we can use to answer practical questions. And of course, I'm presenting on behalf of my group, and which involves several PhD students and postdocs and research scientists. Um, okay. Actually, do you see the full screen? Yes. Yeah. Okay. So, what are PFAS? Have you guys heard about PFAS?
Yeah.
Okay, good. That's good because when I worked on this, 2018, I actually had never heard about it. And many people around me have never heard about it. But now I think because it becomes to the new gets to the news very regularly, and I think more and more people have now heard about it, and people also start to work on that problem. But anyway, when we started to work on that, it was not really a big deal, and was not something that even was considered to be something deep, like sort of in terms of hydrology. Anyway, so PFAS, their acronyms stand for per and polyfluoroalkyl substances, which, for those who do not know much about chemistry, which I was one of them, this doesn't mean much, right? So here I'm showing a molecular structure of PFAS. So you can see there are a bunch of carbon atoms connected with each other. This is the carbon chain, right? This is organic chemical. And then usually you would have hydrogen connected to carbons, but here all of the hydrogens are replaced by fluorine. Okay, so in this case, it's a per, right? So meaning that all of the hydrogen of the carbon chain are replaced by fluorine. If it's only part of them are replaced, it's a poly. Okay, so this is a perfluoroalkyl substance. And then connected to the carbon chain is a head group that turned out to be polar. So it's hydrophilic. So it likes water. And then the carbon tail is hydrophobic and also oleophobic. So it does not like water and does not like oil. And this is a very special molecular structure in a sense that, when you put this type of molecules into an air-water system, they actually would like to hang out at air-water interfaces because the head group can be inside water, the tail can be outside of water. That's where they're thermodynamically happier, right? So the tail does not like water, so they can be outside, and then the head group can be inside water. And so that's why they are called surfactants. They are surface active agent. Okay, and then the carbon fluorine bond is one of the strongest chemical bond that basically they don't degrade under natural conditions. They can still be degraded under like harsh conditions like high temperature stuff, but they usually don't degrade. This carbon fluorine bond does not break under natural conditions. And of course, the toxicological research has still been ongoing, but it has a lot of evidence showing that these stems can be toxic due to long-term exposure at very low concentration levels at the parts per trillion. So this is really a cup of droplet in a big Olympiad swimming pool. And then they are all man-made chemicals. They're not natural. And so we know humans are very creative of generating all sorts of synthesizing all sorts of chemicals. So there at least have been like 15,000 of them that have been used and that have been now, of course, dumped to the environment. Hoshin, please.
Um, it's it's interesting. I never asked this question before, but what makes them toxic? Is there
Yeah, that's
something
a
about this structure? Yeah.
so it's actually very related to two things. One of them is this amphiphilic molecular structure, right? So lipids, I mean, all of the proteins that in our body, they also have these lipid layers, and then when you have this type of molecule coming in, then they would intrude, and then they would then interact with the protein and organs, and they don't degrade that they are not consumed. They would stay in your body for quite a long time.
That's
And
the
that
hydrophobic, oleophobic part. Is that what
Yeah,
you're referring to?
So it's the head group that's hydrophilic, and then the tail that's hydrophobic. So the tail would like to stick with the lipid layers, the
Okay.
bilayers. I mean, I don't know the details of exactly how they cause a disease, but this is one of the mechanisms that they stick to. They interact with the proteins, and so and then also their half-life time inside the body is quite long. They can be like tens of years. Yeah. Okay. Okay. So um, I mean, these compounds were produced around, were created 1940s, right? So almost like more than 80 years, and they have been used for many, many different things. That's why like there were 15,000 of chemicals produced. I forgot to mention that. So the example that I showed is a specific example where you have this like eight carbon chain and then you have a head group. But then the carbon chain can be short, can be long, can be branched, can be various type of variability variations. Head group can also be very type of carboxylic acid, can be sulfonic. Well, there are many many different types you can change the head group and the tail, and that's why you can construct like 15,000 of them by chemical synthesis. And the different chemicals would have different environmental transport behavior because normally when you have a longer chain, you have a stronger surface activity. You tend to more strongly adhere to interfaces and stuff. You're a shorter chain, then you're more mobile. You can migrate to environment much more easily. And normally, when they're used in mixtures because in chemistry, it was found that when you have these cocktails of these stems, the performance is usually much better than when you use single component, right? So normally, whenever you find PFAS in the environment, usually they appear as mixtures because when they were used, they're always almost always in mixtures. Okay, so what are they used for? They are used for, all of this non-stick and stain and water-resistant coating, um, and this nice repelling surfaces, and also food packaging. The juicy and oily stuff. You can have this wrap that can hold everything inside because they repel oil, right? So the reason that we repel is that when you coat this stem on the surface, they have the tail pointing outward, and then the tail repel water and repel oil, right? So it can really nicely hold things together. Um, and the other big thing is that they actually have been widely used in semiconductor industry by changing wettability, of the surfaces. And then the other major use is firefighting foams in airports and Air Force bases. So in Tucson, we have Davis Mountain Air Force Base, and there we have firefighting. So actually, what happens is that normally the contamination does not occur due to firefighting because that usually does not happen very often, right? So you have a jet crash that doesn't happen every, usually several decades you would have one of these cases. What the most contamination comes from regular training. So for the military to respond to this type of fire, this accident quickly, they need to do regular training. So they would have artificial fire, and then they would burn, and then they would then train how to suppress the different types quickly. So this training is usually every few weeks, and they usually do that, over a time span of several decades. And so you basically are dumping these type of foams, the firefighting foams, regularly to the land surface, and then they would then infiltrate to soil, etc. So you see that this white stuff, right? These are mixtures of PFAS, and they become in these foams, and then they can suppress fire very quickly because they can coat the fire with a very thin liquid film, and that separate the fire from the oxygen. Very, very effective. So basically, PFAS are very durable, right? Remember, they don't degrade, but once you coat, they stay there for like decades. So they're really highly functioning and durable, and they of course they also have been used in space because you want these extreme conditions, right? So they are perfect chemicals, really, except that they're toxic. Okay. Um, Okay, we are hydrologists, so we look at this the transport of PFAS in the environment because once we dump them, they are now in the environmental media, and many of the PFAS they dissolve in water because of the head group, right? They are polar, so then they would transport with the water, and the water cycle then becomes relevant. And the water cycle basically drives large-scale PFAS transport. Now, one of the compartments that's very complicated is the vadal zone above water table and below land surface. That's where you have the soil grains packed together. The pore space is not, is filled both by air and water in general. So you would form a lot of interfaces, right? Remember, PFAS would like to hang out at these interfaces. And then their transport behavior becomes super complicated than any other contaminants that we looked at before. So that has been the focus of my group over the past like 7, 8 years, and also will be the focus of the talk today. The complexity comes from the interfaces, the multi-phase partitioning, all sorts of dynamics coming from that. Yes, Hoshi, go ahead.
So it bonds to water at the interface, and we're focusing on its transport through the ground. I'm just curious, does it appear in water in vapor phase? Does it also go into the air and is transported by the atmosphere?
Yeah, yes, it does actually. So again, right, there are like 15,000 of PFAS, right? A lot of them, they are their volatility is very low. Like the ones that I showed, PFOS, they're anionic, so they dissolve in water, and there's almost no partitioning to the air phase. But there are also PFAS that are neutral, so they are not charged, and they can have a partitioning to the air phase, and that was not really paid attention in until maybe last year or 2 years ago. People start to measure them, and nobody has now. There was no data reported about PFAS in the soil vapor yet. There's no field measurement, but there are laboratory experiments showing that they can be volatile, and some of them can have a strong partition into the air phase. We had a paper a couple of years ago just to sort of start to look at these problems, and that's a very interesting aspect that is not very much looked at. So today I will not focus on that, but it is an important pathway of transport. Yeah.
So just curious, so you can't remove it by distillation necessarily from the water?
Distillation meaning that you evaporate water and then what's left in the behind would be PFAS. No, you cannot, because you could actually. This is a very interesting aspect, right? So let's say when you have any aerosols, okay, the small air bubbles, you have a lot of interface. Your PFAS would actually absorb to those interfaces, so they would then transport with the aerosol, and that's actually hypothesized to be why you have PFAS found in like Arctic or Antarctic, because you have this aerosols transporting very long range with the air. And that's also mostly because they are surface active, right? So if they are not surface active, that type of fluid does not contain a lot of concentration. But if you are surface active, then you have a lot of interfaces, then you have a lot of mass at the interfaces. And so, they can actually carry quite a bit of mass. There has been a few studies showing that the sea aerosols, they actually contain a lot of PFAS. And because they have a lot of interfaces.
So just to follow up, if I had water in a pan and suspected it of being contaminated or knew it to be contaminated, I could not just put it through a distiller, vaporize it, and then condense it.
I would not do. Yeah, no, I don't think so. Yeah.
Peishi.
Yes, just follow up on Hoshen's question. In addition to the source of the PFAS into the subsurface, so when it's entering into the subsurface in the unsaturated zone, does it transport with the water as a solute in the water, or it is moves with the water as a insoluble particle?
It's molecule, so it's like a solute. It dissolves in water, but then they also partition to the air-water interfaces.
It also partition into what?
Interfaces between air and water.
Interfaces into
Yeah,
air.
so let's say you have water here, right? So you have PFAS dissolves in the bulk water, but then at the interface, you also have a lot of PFAS hanging there.
So you need a multi-phase flow transporting the subsurface to do the simulation?
If you do not have vapor phase, then you can just track the water phase movement. But if you have vapor phase, right? So if your PFAS also evaporates into the vapor phase in the air, then the air movement is also important. And we actually have a model to do that as well. But today I will mostly focus on the water phase.
All right.
So you would solve some type of Richards equation.
I see. And for the water phase, for the transport part will be the traditional advection, diffusion, and reaction equation for the transport.
Yes, there are a couple of complexities that actually we'll talk about in a couple of slides. Yes, there are a few additional complexities that are specific to this system. But yes, if you formulate a continuum scale, that's pretty much what we have to do, right? Advection dispersion.
Okay, I will ask other questions next.
Yeah. Okay. All right. So I'll start with the field data because I think that gives you an idea. So actually, it was before 2017, around that time, 2018, almost very very little attention was paid to soils, right? So people measure concentration in groundwater. There were quite a bit of testing and measure surface water, and but there was very very little information about soil. And during that time, the United States had a national campaign to measure PFAS concentration in soils at the military installations, like hundreds of military installations. And we get access to the raw data around that time through a collaboration with Air Force scientists, and which turned out to be a very, very interesting finding looking into this raw data. One of them is I'm showing you a compiled data set of PFOS concentration, right? So one of the longer chain PFAS, the carboxygenase 8. And these are, all of them are in the vadose zone above water table, but these are from multiple sites. So some of them have shallower water tables, some of them have deeper water tables. So you can see data points stop at different locations, different depth. And most of the contaminants, most of the sites were contaminated several decades ago. Okay. Now, what do we see here? We see that this is a log scale concentration. Okay. So you will see that despite that these sites were contaminated several decades ago, the vast majority of the mass stays in the first couple meters. Okay, this is our log scale, right? So one grid would be 10 times reduction. So this is really, really like 99.9 something percent of the mass in the first couple of meters. The second is that if you move downward, you see that the concentration declines very fast, almost exponentially. So there's very strong retention in the soil of the PFAS. Then the other thing is that this is the longer chain PFAS, right? So you could also measure the other PFAS that have a shorter chains. If you look at shorter chain PFAS, then they see a different pattern. The shorter chain has a migrate to much deeper depth, and they have more dominance in the shallower than the deeper depth. Okay, so what does this data tell us? This data tell us soils appear to act as a significant source zone of PFAS after accumulating PFAS over many decades. Okay, and they are somehow strongly retained in the soil, especially the longer chain. The shorter chain moved to deeper depth, and this type of pattern is actually quite universal at many different sites. This, it's good a mental picture to keep in mind because actually this helped us to think about the problem. Okay, so now given that at many of the contaminated sites, right, actually the majority of the mass is in the soil. Okay, now the question that we ask is actually, is the stuff in the soil migrating downward? Okay, how fast are they migrating downward? What processes control their downward leaching or migration? Can we develop mathematical models to predict that type of leaching? So those are the questions that guide much of our work in the past 7-8 years, and will be the focus of the presentation today. So here's a conceptual picture of PFAS transport in soils and the associated physical and chemical processes. So PFAS can be released by different type of means, right? Like, industrial sites, landfills, wastewater treatment plants, and also firefighting. And once PFAS are in the land surface, released to land surface, you have different type of rainfall, different type of infiltration events like rainfall or other type of recharge events. Then the PFAS then migrate with water to the vadose zone. If you zoom into the vadal zone, you'll see particles packed together. You have a pore space filled by both air and water and with a bunch of interfaces, and the PFAS would like to stick at interfaces, like we mentioned earlier. They would also like to stick to organic carbon because the organic tail likes to interact with the carbon. And so they would basically accumulate at solid surfaces and air-water interfaces. And the soil has a lot of them. The other thing that happens is that when you have PFAS present in pore water and air-water interfaces, they actually change the properties of the interface. This is also why they're used widely for different things. And so if you have a water droplet and you see that it changes surface tension, they also change the contact angle. Okay, and these are the two properties that actually govern the capillarity of water in the soil. So if you have this capillary rise, right? If you change the surface tension, change the contact angle, the rise will also be modified. And this would then also change the water flow if you have this PFAS in the water system. So it's actually a fully coupled system, right? So PFAS change, water drives PFAS transport. The PFAS also modifies water flow by changing the capillarity. So when we start to work on that, right, this type of system were not really looked at before, and so we need to start from scratch to formulate these equations. But actually, they're not super complicated. They're actually pretty standard things, like Pacey was saying. So first of all, we need to model soil or water flow, right? So we would take the standard Richards equation. But what the complexity with now, in addition to that, is you have your capillary pressure as a function of your concentration. Okay, so we need to account for that. So we account for that by using this lever J scaling to scale the capillary pressure as a function of your surface tension and contact angle, a cosine of the contact angle. And then for the transport, it's the standard advection dispersion equation. There's nothing crazy about that. Because that's pretty much the standard formulation we can use at this scale, at the Darcy scale for side scale modeling. But you do have to account for the partitioning to the solid surfaces and partitioning to the air-water interfaces. And there can be a lot of complexities involved with that. Here, I'm just showing a very simple example formulation so that you get an idea, right? So for the mass in the solid surface, you could have a fraction of the solid surface that's instantaneous. You could have some fraction of that is kinetic. There's a time scale for the aqueous phase to partition to the solid surface. So here I'm showing a simple two-side model. You have an instantaneous and kinetic. You have a fraction between them. This is actually pretty standard also for other type of contaminants. You would use this, and you can use a linear or long linear. Here we use fluently, so it's long linear absorption. The air-water interface absorption is a little bit tricky. So you also can assume you have some instantaneous partitioning, so the aqueous phase can move to the interface instantaneously compared to your transport. But there could also be compartment or interfacial domains where it takes some time to move for the PFAS to move to the interface. So you could actually have multiple, sides, etc. But here I'm just showing a simple formulation for you to get an idea. So you have an instantaneous side and then kinetic side. And then so what's different between the air-water interface absorption and the solid surface absorption is that the absorption sites would change with time, right? So the solid surface, they won't change. You have the organic carbon, that's the amount of sorbent you have. But the air-water interfacial area, if you are fully saturated, you would have no air-water interfacial area, right? There's no absorption to air-water interfaces. But then if your soil becomes dry, you have a lot of interfaces, then you have a lot of partitioning to the air-water interfaces. So that's why, there's an air-water interfacial area, and this air-water interfacial area actually has to be modeled, right? They have to be modeled by some linking to some of the hydrological variables. And one of the approaches is just to link that to the saturation, and that's what we did. But there are also other complications involved that. But one of the simplest approaches is to link that to the water saturation. So you solve the water flow, you can then project your air-water interfacial area, then you can figure out how much absorption you have. Anyway, so this is the standard formula. Yes, go ahead.
You mentioned that the presence of PFAS and presumably the amount of it changes the angle,
Contact angle, yeah.
the contact angle and the properties of the capillarity.
Yes.
So does that Is that another feedback that you're taking into account when you're modeling all of this stuff? Because that changes
Yeah.
also. Yeah.
Yes,
Okay.
that's included here.
I see. Okay.
Yeah, so the capillary pressure would scale with the surface tension and the cosine of the contact angle. Yeah, this is basically assumed the equilibrium, capillary equilibrium at the REV, a representative elementary volume scale. Yeah. So it's represented, but it's represented at this scale, right? Of course, actually I will talk about the all many power scale processes later, but this is the sort of the standard approach we can try to represent these processes. Yes, Lila.
Sorry, one more. And the
Yeah.
integration time step, what are we talking about? Seconds, microseconds,
You mean
hours,
for this type
days?
of field Widow zone calculations?
Right.
Hours.
Hours. Okay.
Yeah.
Thank you.
Do PFAS tend to clump together to create aggregates, or do they repel each other?
That's a very, very interesting point. They do. So actually, if you have a lot of PFAS, the concentration is high, right? So I mean, of course, right? What I described is that you have PFAS dissolving in water, you have PFAS hanging in the air-water interfaces, right? If you keep increasing the concentration in the aqueous phase, what happens is that now you don't have anywhere to have PFAS displaced, right? So you have a lot of PFAS inside your aqueous phase. Then remember, the PFAS, the tail, they don't like water. So what they would find, what they would do, driven by entropy and energy, is that they would form this type of they call critical micelles, right? So they would have the tails point to each other, so that they can then so only have the head group outside, right? It's like I don't know, it's like a sea star, like they have the head group are pointing outward because they like water. The tail can be protected inside, so that they can be away from water. And that's a critical micelle concentration. You have to reach a certain level for that to appear, but they do appear. But normally, in an environmental concentration, the concentrations are much lower, so this won't form. But they could form when you apply AFFF, the firefighting foams, when they were first introduced to the soil. Yes, Jasper.
Thank you, Bo. Just a clarification. That Leffler J scaling, that's based on the Young-Laplace equation, right?
Yes.
Okay, okay,
Yeah.
good.
So basically, the formulation is developed by assuming that the soil can be approximately a bundle of tubes, and each tube is a Young-Laplace equation, and then you assume equilibrium, and then you basically scale the capillary pressure by the surface tension and contact angle.
Yeah, because the capillary height is the linear function of the angle, of the cosine of the angle, right?
Exactly. Yeah.
Yeah. Okay.
This is Young-Laplace equation. Yes. Yeah. I mean, of course, there could be more sophisticated version of it, but the scaling is always pretty much like this. You scale with it's a matter of how you want to account for the process distribution. Yeah. Okay. Thank you for the questions. And so once we have this formulation, this bunch of PDEs, and we solve them fully implicitly because it's a fully coupled system, later we found out that it can also solve it sequentially if you can iterate. And for the environmental concentrations, it's actually more efficient because the nonlinearity is not super strong. But we had multiple numerical frameworks implemented, and we can solve them. And at that time, we actually did not have a field data, a controlled field data that we can compare with. So what we did is to conduct a bunch of numerical experiments to sort of get a handle of what's going on at those sites. And the point is not to predict anything. The point is to really sort of use this as a numerical tool to assess what's important and what's not, and on what conditions are important. And so what we did is that we assumed that you have some type of fire training, regular fire training, and we actually looked into the fire training manuals at these military sites, and then how often they train, how much they release every time, and then how long they release that, and how much concentration they have in the firefighting foams. So these are information we collected. And then we collected high resolution precipitation and ET for Arizona and New Jersey, representing two type of climatic conditions. And then we have access to this soil parameters from my collaborator Mark Rousseau's lab, and also air-water interfacial area as a function of water saturation. So we don't need to model that in this particular case because we don't want that uncertainty to change the system. And then we also have to have a measurement of surface tension, which basically tells you the surface activity of PFAS, right? So you change the concentration, you change the surface tension. This type of curve tell you how surface active your PFAS is. And from the curve, based on the thermodynamics, you can calculate the absorption coefficient. So with this type of curves, then you can then compute the absorption coefficient, and you have all of the things parameterized, and you can run simulations forward with PFAS, with fire training and transport. So the first thing we did is that we conducted a simulation of a 30-year regular training, like every 10 days. You have training activities going on, and then you can see that you have PFOS migrating downward during that 30 years. And then after that, we stopped fire training. So you don't have any PFAS going into the soil, but then you do have regular infiltration that can drive PFAS downward. And so we call that post-contamination. So here we incorporated the absorption to the interfaces. And this is what you see. This is actually very consistent with the field observations where, for decades, your PFOS stays in a very shallow soil. Okay. Now, because we're in the computational world, we can turn things on and off. So we turn off the partitioning to the air-water interfaces. Then we recompute the entire process. And what we see is that we see completely different behavior. Right. So in this case, the PFOS would reach to 4 meters, which is the groundwater table, about a couple of years. And then after you stopped releasing PFAS to the surface, less than about 15 years, much of the mass is gone. Okay. So what does this tell us is that on the first order, air-water interfacial absorption significantly reduces PFOS leaching in soils. Right. Of course, it depends on the parameters that we use for the soils, but in general, this is pretty much the case for this type of video zone simulations. It just changes the magnitude if you use different type of soils. This is a very interesting finding that basically, you use the mathematical model, you can test. This is a first order mechanism that contributing to the retention that you observe in the field. So because you have everything simulated, then you can actually look into where the PFAS is in the soil. So they could be at the air-water interfaces, the aqueous phase, at solid surface, right? So you can guess that probably much of the mass is not at the aqueous phase, and that was the case, right? So in actually more than in this particular sand that we simulated, 98% of the mass at the air-water interfaces, and only about 0.1% is in aqueous phase and 1% in the solid surface. So what does this tell us? This tells us that even though you have a lot of mass in the soil, only a tiny fraction of that is available for movement, for transport, right? So only the water phase is can be mobile, and so this would then suggest that your soil concentration is going to be much higher than the concentration you observe in groundwater, because only a tiny fraction of that soil concentration can be actually migrated to groundwater. And this is consistent with field observations. They see a very, very high concentration in soil, but the groundwater concentration is still very, very small. Okay. So again, that's actually what's promising. We have some, qualitative agreement between the models and then the data. But there's something that I did not tell you, which was on purpose not to distract you. But if you look at the data set, actually, even though the majority of the mass in the shallow subsurface, right? But you do have mass migrating to very deep locations in this case, 30 meters. And even though their concentration is very small, that was not captured in the model simulations that assume homogeneous domains. And we were puzzled. So something must be missing from the simulations that missed this type of sort of migration to deep vadal zone and groundwater. And you do see actually PFAS in groundwater at many of the sites, even though you know the majority of the mass is still in the soil. So what might be contributing to that observation? Of course, as hydrologists, the thing we blame is heterogeneity, right? So heterogeneity must be doing all of these things. And we did that too, and we blamed heterogeneity, and we actually examined that in a couple of papers. So it is actually, so heterogeneity is one of the things that can do that, can basically allow your PFOS to migrate much deeper depth. But there's actually something very unique to the system. So we know that heterogeneity would generate much greater pole order velocities, right? So here's a simulation with generated stochastic heterogeneity. You can see that these are velocity profiles. So you see that you have highly channelized flow, right? So you know that heterogeneity can have this high pole order velocity that can then accelerate transport. But what happens for this PFAS is something even more important. So along the sort of the preferential flow pathways, your soil is wetter. Okay, soil is wetter, and so that you have higher water saturation. What does that mean? It means that your air-water interface area is destroyed. Okay, so along the preferential flow pathways, you have a greater pole order velocity. They can accelerate transport, but you also have much smaller retention, in the sense that you don't have a lot of sites for the PFAS to stick to. So that actually greatly amplifies the transport along the preferential flow pathways. And that turned out to be a very unique phenomenon for these surface active contaminants that you would not see for a regular contaminant, a regular like conventional conservative solute. And this is dynamically impacted by the hydrology. And so that we examine that, we simulate that under various conditions, and that turned out to be quite important. The acceleration can be several times because of the amplified reduction of your retention. Yes, patient.
Oh yeah, Bo. So just like a clarification question. Could you remind me the differences between short chain and long chain PFAS,
Yeah.
and the reason why long chain PFAS accumulate more in the deeper layer of the soil is because they are different properties, so that they modify the soil property in a different way.
Yeah, so long chain and short chain, the main difference is that their chain is different, right? One of them is shorter, one of them is longer. So the ones with longer chain, they have stronger hydrophobicity, so they don't like water more. So they would like to stick at interfaces more. So the longer chain would have a stronger affinity to the interfaces. And that's why they are stuck into the shallow soil. The shorter chain, their chain is shorter, so their hydrophobicity is not very strong. So they're more like a conservative solute. They don't stick much to air-water interfaces, so they can migrate much deeper.
I see. Okay, thanks.
Yeah. But I will not talk about this. This is actually not the main point of today's talk. That's one of the things that we examined that turned out to be quite interesting. But what I'm going to talk about today is some very interesting pore scale processes. So if you zoom into the soil, okay, you see that there are at least two types of interfaces, air-water interfaces. One of them is this kind of bulk air-water interface that we call, like, you have a capillary, like this pendular rain or bulk interface, right? So you have this curve, the interface is formed by the capillarity. And the other type of interface is if you have a soil grain that is dried, but then you have water films covering on that. Okay. In this case, you have a water film covering the soil grain, and then you have a lot of interfaces along the film. So these two air-water interfaces are very different, turned out, for the transport of PFAS. And actually, the thin water films account for more than 90% of the total air-water interface area in soils under field conditions. So they turned out to be much more important than the bulk interfaces. Now, our hypothesis, when we had this conceptual picture, our hypothesis that the thin water films may or may not be accessed by the PFAS during the transport time scale. And in the prior simulations that I showed, because we measure all of the interfaces in the soil, we assume they are all accessible. They all can be instantaneously accessed by the PFAS. They may not, right? So if they don't access all of these interfaces, then the retention will be much smaller, and they can migrate to much deeper locations. So that's one hypothesis. The other hypothesis is actually related to the physical chemistry of the films. So when you have the film very thin, on the order of nanometers, like tens of nanometers, then you start to have the surface forces acting. So the soil grains are usually negatively charged, and the PFAS, many of them are charged. Some of them can be positive, some of them can be negative. For the negative ones, then they could have surface force interaction, and then that can actually reduce their absorption to the films compared to the bulk interface, which I'll talk about later. So these are the two hypotheses that we formulated, and we want to test and whether they actually influence the transport of PFAS in the soil, in the unsaturated zone. Let me see how much time I have. We actually went quite slowly. But I'll I think the most important part is to get the idea, and then the details, we can go faster. Okay, so we're going to first look at the first the film mass transfer limitation problem. So imagine you have PFAS coming downward. You have them transport in the pore water. They can easily access the capillary interfaces, right? The bulk interfaces. Now, for them to access the film interfaces, what do they do? The films, normally there's not much advection. It's pretty much diffusion. So the PFAS have to diffuse along the films to access the interfaces. That's also what we thought about. And the other thing that worth mentioning is that, so here you have this bulk water connected, right? So if you have, some of the pores that are drier, then you see that this actually bulk water become disconnected from the other cluster of bulk water. And this would happen more often when you have drier conditions. So you have this type of island bulk water that are not connected to the cluster. In this case, then also you create a cluster of films that if you want to access them, you actually have to climb multiple films to access those film interfaces. And that turned out to be also something important when we think about the mass transfer limitation of PFAS in the films. So our original idea when we thought about this problem, was that the films, under drier conditions, or the film become very thin, like tens of nanometers, or like less than 100 nanometers. The diffusive flux, the aqueous diffusion flux, right, would scale with the thickness. Okay, when your film becomes thin, the flux would almost drop to zero. So that's our hypothesis. We assume that the films cannot be accessed at all under drier conditions. And then we formulate this transport, we formulate pore scale formulation, we developed that, and we actually finished everything and wrote the paper and we actually were about to submit. But then I read some literature from this fluid mechanics and surface science. And it's something that's very commonly recognized in their field, is that when you have this surfactant adsorbed to interfaces, they actually can also move along the interface driven by chemical potential gradient. So in this case, if you have PFAS absorbed to the interface, they actually also can diffuse along the air-water interface. Okay, and this diffusion is then a two-dimensional diffusion. It does not scale with the thickness of the film. So no matter how thin your film is, you always have this surface diffusion along the interface, and this is almost independent from your drier or wetter condition. It always have a two-dimensional diffusion. So you can imagine this would probably greatly increase the mass transfer flux of PFAS going through the films. And that's what we thought too. So we incorporated that, and that completely changed the results. Okay, at least under some of the conditions. So here's how we did it. There are a bunch of details of how the models are formulated, but we formulated a pore scale model that represented this transport between bulk water and film water, and this aqueous transport and surface diffusion, etc., under drier and wetter conditions. And then these pore network models then conform to, let's say, you can conform to a soil microcity image, so that their topology are captured. You only simplify the pore structures, and then so that you can compute things analytically within a pore space. But anyway, we construct this type of pore network, a digital representation of the soil, and we can operate this physics through this digital representation. But we don't want to have a random pore network. We want to make sure our network conform to specific measurement. So the pore network can generate the soil water characteristic curve. We make sure that it can match the measured soil water characteristic curve. And then we also make sure that interfacial area as a function of water saturation match with the measurement. So this pore network is not a random network, it's actually conformed to a specific sand medium that we use. And now, we can then run simulations by solving these equations. I'm just going to show you a very simple scenario. So you have a pore network, and then you inject a pulse of PFAS into it. And here we assume constant water saturation, like 0.5 inside the network. Of course, you have heterogeneity inside the network, but overall saturation is 0.5. And now here are the results, right? So if you assume long reactive solute, you get this gray curve, right? Basically almost no retention. But then if you use the prior model, meaning that you assume all of the air-water interfacial area can be instantaneously accessed, you would see this orange curve. You have very strong retention. Okay. Now, if you then account for this mass transfer between the film and bulk, but you do not account for the surface diffusion, okay, this diffusion along the interface, then you would get this this dashed blue line. That's very similar to the conservative solute. Why? Because in that case, you almost access none of the interfaces, and then you only access the bulk interface, which is a tiny fraction. So you're more or less a long reactive solute. That's why you recover the gray curve. Now, if you then incorporate the diffusion along the film interfaces, then you can you actually become the green curve. You're very close to the prior model that can access all of the films. There's still some mass transfer limitation, but you can access much of that. Okay. Now this is under a pretty wet condition, 0.5. But if you look at a drier condition, then you see that we see a different picture, right? So 0.3, and then you see that in this case, even if you account for the surface diffusion, you still have a strong mass transfer limitation into the films, because the reason actually is that when you're under drier condition, you have a lot of the bulk water disconnect, and actually you have this cluster of films. You have to climb multiple of them to access them, so the travel distance is much longer. And so then in this case, you have strong mass transfer limitation, even if you have surface diffusion. And so what we found that this film regulated process turned out to be quite important, and we're now incorporating these processes into the formulation that we showed earlier, the standard formulations, right? Because pore scales is useless for field scale investigation, so we have to incorporate this, and this is upscaling. Right. So we have a paper just recently published last year that incorporated some of this in the formulation. I think so. How much time do we have?
Actually, we usually continue our discussions for quite a bit of time afterwards, and people just sign off as they have to go. So take your time. Yeah.
Okay. All right. Well, I mean, if you become bored, let me know so that I can shut up.
We're definitely not bored. So I'm learning so much from hearing you. You explain things in such a beautiful and clear way. I'm amazed. It's beautiful. Thank you.
Yeah. Thank you. Patient, you have a question?
Yeah, so if we have enough, infinite amount of time, I'll just ask questions. So I've heard of the network, what is that? Pole network
model, yeah.
Yeah, but I'm not quite familiar with that. How is different from the continuous form you formulating the
Yeah. So let me give you a very simple explanation of pore network model, right? So basically, if you look at the pore space, right, of the soil grains packed together, here as an example, right? So you can think of this as a pore body, okay? And then you have a sort of a very narrow space between the two grains. Usually this can be approximately the throat. So you basically have a bunch of pore bodies connected by the throats. Use that to approximate your pore space. Okay. Now, if you do that, actually, this model is still full representation of the pore space. The simplicity that comes from this pore network model is that you don't actually represent the pore space exact, right? You don't represent this pore body exact. You assume that it's some type of ideal geometry. You use a cube, or you use like a square tube to represent the pore body, and then you use some type of regular geometry to represent the throat. Okay, but you do maintain the topography of this big pore, small pore, and the aspect ratio, all of that. So that's why this type of pore network model, you can actually replicate the soil water characteristics curves, right? So it's still a porous medium, but it's simplified within each pore and pore body and pore throat so that you can calculate things analytically. You can do equilibrium. So here's another assumption that's very important for the pore network formulation, right? So in principle, what you should do is that for a pore body, you actually have to discretize the pore body to solve a Navier-Stokes equation. Okay, so pore network model does not do that. It assumes that within one pore body, you assume chemical and mechanical equilibrium. Okay, so basically within this one, you don't solve numerically. You just assume it's equilibrium, so you can formulate things analytically. So if you look at a pore, like a square or pore body, which I think I showed earlier, here. Yeah, here, right? So if you have this type of a square cross section, right? Because you assume equilibrium, you actually know exactly where the water is. The water will be at the corners, right? And then you have films covering the solid. So you can actually exactly compute the configuration of the air-water interface if you know the total saturation inside the pore body. Okay, and then if you have a bunch of these pore bodies like this, you can then, based on capillary pressure, water pressure, you can transport fluxes. Right? Based on that, you can propagate the air-water interfaces, etc. It's a simplified representation of two-phase flow in porous medium, but then it's still fine enough that captures the impact of the pore structure on the overall flow and transport.
Okay, so this representation can be solved both the flow and the transport.
Yes, yeah. Two-phase flow. We also have dynamic two-phase flow of that. Yes.
Okay, I'll next.
Yeah, Hoshin, please.
Just a quick extension on that. So you're making assumptions about the geometry of the connections and the shape of the thing, which makes perfect sense. And your results are suggesting that those assumptions are okay as long as you represent the broad architecture
of the pore space.
distribution. Yeah. Right. I'm just curious because you could make different assumptions about the shapes of these things, right?
Yes.
I'm just curious if anybody has done anything where they've randomized those things and whether that makes any significant difference.
Yeah, we actually did that. You remember Sidian's work, right? So we explored different type of geometries and turned out they were not super critical.
Okay.
The overall behavior doesn't change much as long as you maintain the aspect ratio. And so basically, so what happens with this type of systems is that if you aggregate, they start to emerge, and the details appear not to be a major deal.
Because you're looking at a larger scale than the...
Exactly. What really matters is the distribution of the sizes and the connectivity.
So from just approaching this from an information perspective, you're saying, what are the factors that matter and what are the factors that could be sort of ignored in some lossy sort of sense, but that are not going to make a huge difference. Yeah.
Yeah, I mean, of course, it depends on systems, but for the system we looked at, it's what really matter is the connectivity and size, and of course local geometry. But then as long as you account for the capillarity locally, then usually you can reproduce the global behavior. Yeah. Okay. So let me just start the second part of it, which is actually very interesting. So I mean, the pore network model, right? So we were sort of naive in the sense that, okay, we accounted for the film diffusion, aqueous diffusion, film surface diffusion, but actually there are other processes that are happening along the films. One of them is this. One of them is that when you have the surface tension change, right? Remember the PFAS also change the surface tension. When you have the surface tension change, you generate a stress at the interface. So they can then actually move the fluid because of that. And that was not accounted for in our framework. And this is actually a well-known effect in fluid mechanics called Maragoni flow. By changing the surface tension, you can move the fluid along the interface. Basically, it's surface stress, right? Surface stress, and that drives the fluid. And this is one of the processes. And this is how it works, right? So when you have higher concentration, you reduce the surface tension, then fluid moves from a low surface tension to high surface tension. And the other process is that, so remember, many of the PFAS are charged, right? So when they're dissolved, they're charged. And let's say, PFOS is negatively charged. And we have PFAS negatively charged, and you have the green surface most of the time also negatively charged. And so then these are a bunch of ions that they interact with each other. Those electrostatic forces also play a role when you have a film very thin. So then these also can generate migration. One of the mechanisms is called electromigration, driven by electric forces. And this was not accounted for in our framework. And so what we did here is develop a coupled model to look at this specific film transport with this Maragoni flow, surface diffusion, aqueous diffusion, and also the electromigration. So you would then formulate hydrodynamics for the film. You formulate transport, aqueous transport, interfacial transport, accounting for the different forces. And then you also need to solve the electrostatics in the vertical direction. We apply lubrication. So assume there's a separation of scale, and then you can then reduce this to a two-dimensional problem instead of solving it in 3 dimensions. And then, but we also define dimensionless groups because there are multiple mechanisms that are happening. We define 3 dimensionless groups. One of them is a Peckley number that defines the advection versus diffusion, and then electromigration, which is the electromigration versus the surface diffusion. And then also the ratio between the, basically you could have background film flow that can be driven by gravity or can be driven by Maragoni flow. So they also take a ratio between that. And then there's a bunch of analysis behind this, a lot of work, but then basically, we showed that these different processes, they actually do matter in certain parameter space. And if you do not account for them, they can lead to different results. But what matters is not that. We know that. What matters is the regime under which we have to account for these things. So we develop a regime diagram based on the 3-dimensional numbers. So we can then basically, based on the asymptotic analysis, you can decide on under which range of the dimensionless number, which of the processes is dominant process. And so that if you can develop such a regime diagram, then it can guide you to say, well, can I ignore certain processes for my parameter space? And this is what we did for that. And you could also let's say if you don't account for this basically the background advection, right? So normally the Maragoni flow is going to be much greater than the background advection. In that case, then you only look at a 2-dimensional regime diagram. Then you only have 4 of the regimes and with a transition regime. But anyway, these are like classic fluid mechanics analysis that we have done, and it turned out to be quite useful. This type of a regime diagram that we can use to assess conditions under which, and this is one of the applications of that. So let's say if you look at field conditions, you have 100 nanometer film thickness, and you have a concentration about less than 10 milligram per liter, then you can start to compute the dimensionless numbers, and then you can see whether whether the different processes are important for this particular problem. And we did some of that in the paper that's still on review. Okay, so that was the film transport limitation, right? So the other part is this absorption at the films, and I'll explain the idea just very quickly. So if you look at this film, right, this is a film water covering the soil grain. The PFAS is a negative charge at the air-water interface. You have some also in the aqueous phase, and then you have some electrolytes in the air-water interface, right? In the film, the soil grain is negatively charged. Okay. Now, what happens is that you would have because the solid grain is charged, right? So they would attract the positive charged ions, right? The counter ions, and then similarly the interface, this also negative charge, it would also attract the positive ions. So you would form a electrical double layer that's widely known in physical chemistry. So you would basically form an electrical double layer in the solid surface. Okay, meaning that you attract the counter ions, and then at air-water interface you also form an electrical double layer, And it can go and on with different complicated processes. But what happens is there is always a thickness attached to your electrode double layer, and that is called the bilength. You can actually calculate the characteristic length. If your film thickness, the thickness is on the same order as that thickness of the electrode double layer, then you would have the two double layer overlap. Okay, meaning that then basically the solid surface would repel the airwall interface. If you have PFAS negatively charged, the solid surface negatively charged, you would repel the PFAS. So what happens is that basically, for the PFAS in the films, your chemical potential, you have an extra contribution of your chemical potential, which is the electrostatic interaction. So you don't need this amount of PFAS at the interface. You can have a fewer amount to have the same chemical potential compared to the bulk interface. So the net outcome is that adsorption at the film interface will be smaller compared to your bulk interface for the same chemical potential, because you have an extra chemical potential that comes from your solid surface. So that's one way to think about it. The other way to think about it is that basically you're repelled, right? You're repelled, so you have to move somewhere. So your concentration has to be reduced in that regard. And we actually also did molecular dynamic simulations, and we showed that at the interface is charged, and you do have this type of effects showing up. And so it also works for PFAS with different chain lengths, etc. So that's basically the concept I explained, right? So you have an electrical double layer for the solid surface, you have an electrical double layer for the airwall interface, and they start to overlap. And because of that, then you repel the PFAS so that you drive the PFAS from the film to the bulk interface. And then so you for the same aqueous concentration, the density, the mass density at the airwall interface is going to be smaller than the density at the air bulk interface. So actually the absorption to the films is going to be smaller than the bulk interface. And this would lead to also reduced retention at the airwall interfaces. So there are a lot of details that we formulated, the chemical potential, and try to solve these systems, and they can be done. There's a lot of physical chemistry here. We have to read a bunch of books from surface science to solve these equations, but it was interesting. So you can solve them, and once you solve them, you can then start to assess the deviation. We call that anomalous absorption, meaning that we assume the bulk is a standard absorption, so the films have some anomaly because of the presence of the solid surface. So then you can then compute the absorption at the airwall interface as a function of your aqueous concentration, right? So for the bulk interface, you would have this type of dashed line, right? So your absorption will increase with your aqueous concentration. And if you have a thin interface, you would have this solid line. So you can see that it's lower. Okay, it's actually quite lower because the vertical axis is the log scale. Okay, so if we compute this, we actually take a ratio of that, and the film absorption is only about 1/3 of the bulk absorption for this parameter set that we computed, which is under relatively dry condition. So under wetter conditions, actually it doesn't matter. Under wetter condition, the film is very thick, so the thickness is much greater than the characteristic length of the electrode double layer, so they don't really interact with each other. But under drier conditions, this is something important that would change the absorption. And of course, this characteristic length of the electrode double layer would also change with how many electrical ions you have in the interface, and then the film thickness, and also the charges of the solid surface, and we analyze all of that. And in the end, we can actually define also a similar type of framework, right? You can define sort of a parameter space, and you can figure out conditions under which this becomes significant. And this is what we did. One of the axes is charge density, and one of them is the dimensionless water film thickness, which is normalized by the characteristic length of the electrical double layer. And then we found that if you define the anomaly as 25%, then you can find that you can define a critical water film thickness, and below that, then you have anomalous absorption. Above that, you don't. And now, how does this compare to actual with video zone conditions? If you have a metric potential that's -100, then you're safe, right? You don't need to worry about these things. but you have a matrix potential of -500, then you do have a fraction of your parameter space that you could have this anomalous absorption happening, and it may need to be accounted for. Okay, and then we also tested that with some of the experimental data that conducted by our collaborator. And so there has been some experiments. Of course, when the experiments are done at higher water saturations, usually they have very good match. But on lower water saturation, there seems to be some discrepancy. And we basically applied our model to this system. And if you have a standard model, you have this type of curve. But then if you consider this anomalous absorption, then you are closer to the data. They're still not completely match the data, but it gets much closer to that. There might be other factors that contributed. But again, this is very limited data set at lower water saturations, because lower water saturation is very difficult to conduct the experiment. It takes a long time because the retention is very strong, right? So it takes a long time for the experiment to be completed. So most of the experiments are conducted at very high water saturations that are not realistic for the field. But this is one of them, and we showed that for this particular one, it appeared to improve the model prediction. Anyway, again, right, we're interested in these details, but then our goal is also develop practical models for field use. And over the years, we have developed this PFAS leach that span a wide range of model complexity and computational cost input parameters. And these are all formulated at the continuum scale, right? The Darcy scale or represented elementary scales. And these include the full three-dimensional model on the right, a one-dimensional numerical model, and actually one-dimensional analytical model that has been implemented in Excel and Python, and also an algebraic model at the bottom. And this now has been widely used, and you can guess which one has been used most widely.
Tier 4?
4 and 3. Yeah, nobody really uses 1. I mean, researchers like us will use 1, but tier 1, but like the industry never used 1. Nobody has asked me about the tier 1. And there are some people asking me about tier 2 now. But basically what, and this Excel tool actually turned out to be widely used. Like I receive emails almost every week, not only in the US, also in Europe, in other parts of the world, and by regulators, by consulting firms, and by even law firms that are dealing with this litigation. So that's something interesting, right? So no matter how detailed work that you do, it has to be distilled to very simple stuff people can actually access and use. Anyway, so actually the PFAS, specifically the PFAS leach Excel tool, is actually recommended by the U.S. Air Force as actually the only process-based model for evaluating soil to groundwater leaching recently. Yeah. So I mean, there's still a lot of work going on of how to integrate in this detailed film and interfacial process into continuum scale models, and we are just beginning to do that. And one of the approaches to use this type of multi-continuum, dual continuum framework. And so we did a little bit of this exploration in a recent paper. So basically, one of the ideas to treat the bulk water as one continuum and then the film as another continuum, and they have mass flux between them. And you could then write equations for this. And this, by the way, these are widely used previously whenever you have this type of domains in your system where they involve different time scales, right? If you have a fracture and matrix, you would have a matrix as one continuum and then fracture as one continuum. Fracture is faster continuum, and then the matrix is slower continuum. So we're applying similar framework to this system where we treat the bulk water as the faster continuum and the film water as the slower continuum. And then you have to figure out the fluxes between them. And this is basically if you look at the homogeneous domains, you can do that. And if you have a heterogeneous porous medium, then you have to have a multi-continuum because you have to split this both in the fracture and also in the matrix. So that's the approach that we're taking to upscale this. But there's a lot of things that needs to be done, like to parameterize these formulations and to validate with experiments. And so there are a lot of interesting things that could be done, and we're also looking for collaborations with people to move these things forward together. I think I'll end here. So basically, I mean, I've spent quite a bit of time going into many details, but what we learned is that basically the PFAS actually is not just another contaminant, right? They are actually turned out to push the boundary of subsurface hydrology and porous media physics, because there are many processes that we normally don't consider, right? So if you ask me 80 years ago, whether the films are important, I would say no, because the mass of the films is tiny. Okay, if you have solute in the films, the mass will also be tiny. So they're not really relevant for transport. But this conceptual picture is completely changed if you look at surface active contaminant like PFAS, because actually turned out the majority of the mass would be in the films if you reach equilibrium, right? So you cannot ignore that, because that's the majority of the mass. It's not the minor fraction of the mass. So after working on this problem for several years now, I think it's really a rich problem that is not only solving a practical problem, but it's also pushing our field forward in terms of this additional physics that needs to be incorporated in the hydrological formulations. With that, I'll end here, and happy to discuss. Yeah, thank you. Pei Shi, I think you raised the first.
Okay, nice. Thanks. It's a very great presentations. And I appreciate that at the beginning of the talk you mentioned you're not a chemistry person. Eventually you basically walk into the field talking about a lot of iron stuff. I appreciate that eventually you enjoyed it. I'm not a chemistry guy. I never enjoyed it. Anyway, could you go back to the slide 35 that you showed the kind of the trade-off between the complexity and the computational time? Here, slide 36 actually.
Yeah, this one. Yeah.
Right. So you talk about the application of in some of the slides you mentioned the PFAS observations in the field are very limited. Okay, and
that was before 2020. Yeah, before 2020. Now there are way more.
But still, if you want to perform simulators through a continuum form, you have to prescribe the initial condition, boundary
Oh,
condition,
yeah, of course.
right,
Yeah. So they're sparse. They are more sites are measured, but every site is sparse. The data is very sparse.
And does this sparse observations say at each site, does the observation supposed to prescribe a satisfying initial boundary conditions to run the model?
Yeah, so you actually nailed the point, right? So the reason that nobody asked me about this 1D, the tier 1 3D model, is because they have not reached to a point that they have enough information to populate such a model. And so, I mean, I'm not sure if you guys have been to field sites. I've been to many, and I've worked with the consulting firms. Let's say for a contaminated site, that is, let's say, on the order of 100 meters in each direction. How many measurements do you think they have? They have a few soil borings, usually within 5, right? So they have soil borings at 5 locations. And then they have maybe a monitoring well that monitors the groundwater table. And within the 5, these 5 soil borings, they, normally research labs would do a full characterization, but industry labs, they just measure the soil grain surface, the grain distribution, grain size distribution. They measure PFAS concentration, but they don't measure the full profile, right? They would sample maybe 2 or 3 locations or like mix. So you don't really have a lot of information to go with. And even though you have these sophisticated models you can use, but the data is usually very limited, unless you can then justify saying, oh, you have a very strong heterogeneity in your site. If you don't understand that, you're gonna be completely wrong for your mass discharge from soil to groundwater. Then you can justify additional characterization, which will take more budget, right? So, but in a standard, consulting firm, they're working at a site, that's pretty much what they get. And do you know how much budget they have for modeling? A couple of days of a person, right? So they cannot afford very complicated models.
Okay, then that leads to another question. So in some of the previous slides, introduced a lot of different empirical equations to describe different relationships. I kind of lost because again, I'm not chemistry.
You mean which part?
Well, just some of the part you have some of in empirical equations describe some of the relationship, but anyway, it will introduce additional parameters. Just still go back to the slide 36, right? By introducing more additional parameters, but at the same time, your observation is still limited. It's basically echoes back the traditional groundwater modeling problem. It's a trade-off between the model complexity, the computational cost, and the availability of the observations.
That's
And
yeah. So I think yeah. Go ahead.
yeah, I don't know. I mean, how you normally solve this problem, this kind of problem.
So I think you're talking about the upscaling part, right? When you upscale, you have you mean the parameters that it may be empirical parameters.
Right, you have a lot of empirical parameters to describe the new relationship you introduce here. You think the PFAS might play a role in the transport and the flow. It's on one hand, it will provide more explainability to the physical process, but on the other hand, the new additional parameters will increase
Yes.
the complexity of the model.
That's right. Yeah.
Has originally been hard to be optimized.
Yeah,
given
that's a
the
very, very good point. Yeah, so I think you're referring to the upscaling, yeah, because before that there's no empirical stuff. For the upscaling, right? So we have to, so now we know the films are important, right? So how do you incorporate that in a continuous scale model? If you don't incorporate that, you're gonna be very wrong. So the question is how to incorporate that so that you at least have parameters you can change, so that you can assess whether this plays a role or not. And I agree with you, right? So basically, the system is already yield parameterized, right? Because you don't have the information to supply the parameters, and then you are adding another parameter or another set of parameters to the system. So I think my argument to that is it is a first order factor. It has to somehow conceptually incorporate it, right? And to what extent specifically how it can be accounted for. So for example, the Excel tool, right? So Excel tool that we had is a new analytical solution that we derived. And in the analytical solution, there's a parameter called airborne interfacial area and absorption, right? So if you know that let's say the airborne interfacial absorption is important, the airborne interfacial area is important, and then that parameter is going to propagate into the outcome. Right? You do have an additional parameter, but you do have also additional process. And it turned out for these systems, this is probably one of the first order factors that controlling your behavior from soil leaching to groundwater. So I mean, I don't think I have an answer to that, but so far what we have worked on is that they turned out to be first order. So you have to somehow account for it. But again, right, the entire system of subsurface is always basically lacking information. So you always don't have a unique theme. So actually, one of the themes maybe I should point out is that the Excel tool actually allows you to do sensitivity analysis and Monte Carlo, right? So this actually allows you automatically generate a bunch of Monte Carlo simulations. So your parameters have uncertainty, and then if you have Monte Carlo sampling, then you know what type of range you could expect. And that actually was a suggestion from the industry. Like when I showed them this, and they say, well, you definitely have to incorporate some type of uncertainty because whatever parameters we input, we don't know for sure. So that was one of the approaches that we took in response to that. But I mean, this is the problem not solved yet.
Yeah, thanks. Yeah, I understand it's a challenge and you have to do some analysis. Thanks. Yeah.
Yeah, I think there are Joseph, right?
Yeah, hi. I guess my question is half for Jonathan and half for you. I'm wondering, with the new build outs of data centers, how much PFAS is considered there. Is that an issue or not? Not really.
Data centers meaning that they need a lot of electricity.
They need a lot of water to cool
to
down
cool
systems. I'm not sure if they're
the
also
system.
contaminating any systems as well. Just curious about that.
Yeah, I know that Tucson, there's a lot of discussions about building a lot of data centers. Yeah, I think, whenever you use water, I mean, for example, one of the things I did not talk about, which is reclaimed water, right? So the wastewater treatment plants, you treat the water, then where do you deliver the water? What happens is that the treatment plants so far are not designed to treat PFAS, right? So in the wastewater streams, you always have PFAS in entering the wastewater treatment plants, but they are not treated. So the reclaimed water would have PFAS for many decades already. So, wherever you are releasing that water, you're introducing contamination to the environment. And some of them is direct discharge to rivers. In Tucson, we have some of that. Some of them is recharge to groundwater. We also have that in Tucson. So we actually have some data sets showing that at the recharge site, the reclaimed water, like managed aquifer recharge, they have the video zone being contaminated by having a lot of PFAS injected to the video zone. So, I think and also you have you have solid left after you treat the water, you have this in the wastewater treatment plants biosolids that also has PFAS, and that has been widely used for agricultural uses, and so that also introduces PFAS to agricultural lands. That's another major source of contamination that is still being investigated. I don't know much about the data center. Maybe Jonathan, you can comment on that.
I actually have so my colleague here in the geology department does study PFAS and is doing contaminant work for data centers. He's part of this project I'm involved in, and PFAS has not come up. So if there is PFAS contamination from data centers, we're not aware of it. But it's mostly heavy metals and thermal pollution from the data centers that we're looking at.
I know that semiconductors, like the chip factories, they use a lot of PFAS, and they actually are exempted of using them. Like they can still use them because it's a critical sector. Yeah, I think Jasper.
Thank you, Bo. The question was already asked by Pesci about, but let me reformulate. I also give this opportunity to tell you excellent work. I started out doing a lot of soils work when I was a student in Amsterdam. Started out with these outflow experiments to determine hydraulic properties. And so my question is related to that, and you already addressed it essentially, but I was wondering, have you done any sensitivity analysis, meaning we know that in describing fatal zones that the heterogeneity of the soil water characteristic, the hydraulic conductivity function are so large essentially, and that's so difficult to characterize. So how important and that is relative to the parameters in your PFAS model in terms of a sensitivity analysis, like what dominates in terms of, you use the word first order, but if you look at the parameterization, the uncertainty in the hydraulic characterization, how important is that relative to your PFAS characterization?
Yeah, that's a very, very interesting question, right? So we actually showed that in the heterogeneity simulations. So people have characterized some sites, so they get the correlation stuff, the geostatistics. We take that and we generated random fields, and we simulate that. We found that because of the heterogeneity, coupled with the interfacial properties of PFAS, these interfacial processes, you can see some actually emergent behavior that you would not see for conservative contaminants. So the heterogeneity, of course, we know they're always important for soil transport, but they're especially important for surface active contaminants because of this weather pathways and that destroy interfaces. And so they actually have to be together. So both of them have to be accounted for to be able to represent this type of behaviors. And so, my advocation to the field sites is that they should always try to incorporate, characterize their heterogeneity, because it could be one of the first order factors that could control your mass discharge from soil to groundwater. But these things are hard because it needs a lot of data.
Yeah, so another question I had, so when you do experiments in the lab to get some of these PFAS properties, surface tension, contact angle,
Yes.
relationships, we know that that holds at the scale of your lab experiment. But
Yes.
then when you embed that in your physical model, which operates at a larger nodal distance,
Yes.
then you usually need some type still of parameter estimation to because when you take the parameters from the lab
That's right.
experiments in your
There's a
model
scaling
and
issue.
to field data, it's not going to
Yeah.
match. So can you comment on that?
Yeah, there's definitely a scaling issue. Yeah. So one thing I did not mention here, which is actually fortunate, is that the surfactant-induced flow, like the change of surface tension and contact angle, we found that they are not important at all. And the reason is the following. So we accounted for that. We actually simulate even homogeneous conditions. They don't matter at all. Why? So when let's say when H2F foam, like firefighting foam, are released, right? They have super high concentration, like usually close to this critical micelle concentration. Because they want to use this harsh heat, right? So they can create films and covering and separate fire and the fuel. But once they enter the soil has a lot of interfaces, airway interfaces. So much of the mass go to the interfaces. The polar concentration actually dropped by order of magnitude, so usually 2 or 3 order of magnitude. So if you look at the soil concentration, the polar concentration is usually several order of magnitude lower than the firefighting foams. So the change of surface tension is actually not huge.
Okay.
It's usually pretty small. So actually one of the reasons that we can do tier 3 is that we can do analytical solution because we know the coupling is not important. So you don't have to couple the flow and transport if the surfactant-induced flow is not important, so that we can solve this equations analytically. So that's actually one of the interesting things, because to be honest, actually, when we first look at the problem, we thought, there's a lot of cool nonlinear analysis you can do, and we were very disappointed finding out that it's actually not important at all, under field conditions, even for fire training area sites, right? So if you look at biosolid sites, the concentration is even several order magnitude lower. So this is even not in the picture. But so, and because of that, then you can simplify that. You can solve flow separately and then solve transport. However, your question is still valid because we still need to parameterize the air-water interfacial absorption. Right, so we need to then the air-water interfacial area, the amount of air-water interfacial area, that you have to determine amount at the scale that you apply the model, right? The grid cells, like centimeters or tens of centimeters or meters, and that is a big problem that we haven't resolved yet. So one of the approaches that we're taking in collaboration with geophysicists, actually Lee Slater from Rutgers. So we're looking at basically using geophysical measurement to then correlate that to airway interfacial area measurement, and then somehow develop some empirical relationships to sort of characterize the heterogeneity of airway interfacial area in the subsurface. But if you don't do that, right, so you don't have the information to populate. So that's one of the potential approaches to address it, but we haven't really, got the results yet. It's just the project that started early this year.
Okay. So let me ask one last question, more technical. So I saw in your paper you use a Richard solver, but you decided that you don't use Picard iteration, you use Newton-Raphson, right?
Yes, it's
And
actually.
What is the reason for Newton-Raphson and not for Picard?
Yeah, so I implemented it myself, right? So And so Picard iteration has because it does not use the gradient, right? So only lacks the coefficient. So it's
Yes.
first order convergence.
Yes.
And Newton-Raphson is second quadratic convergence. Yeah? So it converges faster.
Yeah.
It doesn't really matter much for the system that we deal with. But for certain extreme conditions, when you have soil super dry and you have water infiltrating, and there your gradient could be messed up.
Yeah.
And so what we did in our system is that it's a basically numerical trick, right? So you do not allow the soil to be completely dry. So you set a threshold, and then so that you don't go to these regimes where your threshold, your gradient becomes crazy. But then this does not actually impact the final result because that threshold is tiny.
No, I
So
was really happy to read that actually. But the only disadvantage is it's more work because you need the derivatives as well. That's why Picard iteration people implement it, but it's numerically not as stable. Certainly not for, infiltration in really dry soils, like sandy soils with suddenly rapid amount of water, and that's numerically really unstable, certainly with Picard. So I was really happy to see that. So thank you.
Yeah. So actually, so you have a very good point of that we have to build the Jacobian, right?
Yeah.
So we actually use automatic differentiation in our coding. So
Okay.
that actually comes naturally. So we
Okay.
write the residual, and then automatic differentiation delivers the Jacobian directly.
Okay.
Yeah.
Yeah,
So I
you can
mean,
do that analytically still, probably.
well, for our system we couldn't because a lot of nonlinearity. You have to do a lot of manipulation. Yeah. So we did not do the analytical Jacobian. We just did the automatic differentiation.
Okay.
Yeah. But I also have done this sort of hand building of the Jacobians in the old days, and that's a lot of work. With this residual with automatic differentiation is much, much easier.
Yeah, I think this is an interesting topic. Also, Hoshin as a student, that is actually as a next step, if we can build a Richard solver with an OD implementation where we get the gradients automatically, I think that's a very interesting research topic because that would help you. But there's also many people in hydrology that
Yeah,
would benefit from that type of implementation, and I think that's possible. It just requires a little bit of research.
that's right. Yeah. So the AD definitely, I think, is the future for PD solvers. Yeah.
So, thank you, Bo. Excellent work.
Yeah. Thank you, Jasper.
Leila?
Okay. So I have two questions, and the first one is related to real soils because you already have the tools for tier 3 and 4, and I was thinking about how to move from relatively granular media to actually clay-rich soils. Do people can use it regardless the type of soil?
Yeah, so the equations are written for like general soils, but with the complexity comes. So there's one thing that will become deep challenging for clay-rich soils is for the parameterization. And when I say that, that's really the airwater interfacial area, right? So for the sandy media, I didn't really go into any of the details, but so remember, there's airwater interfacial area, right? So that's something that will change depending on the hydrological state, meaning the water saturation and the capillary pressure. So it has to be somehow modeled, right? It has to be somehow modeled. So the current model that we use is this energy-based method that assumes that basically if you get the soil water characteristic curve, you can then use that curve to integrate to get airwater interfacial area based on energy balance. And this approach has an issue, meaning that it does not account for the grain surface roughness. So it assumes basically the grains are smooth. And so that any media has some roughness, and so that basically would increase the airwater interfacial area because of that. So there has to be some type of scaling factor to scale it up, right? So you use the water characteristic curve to compute the airwater interfacial area, but then you need to scale it up to account for the roughness. Now, this scaling factor, we don't know. So it has to be somehow determined by experiments. And so there are measurements of aerial interface area done for a few media. I can actually count maybe less than four, right? So specific sand media, and in the entire literature, right? So over the past several decades, and that has been used to develop a scaling factor for sandy media because it was only measured for sandy media.
Mhm.
And it's expected that this scaling factor will be much bigger for finer grain soils like clay, but we
Mhm.
don't have information to obtain the scaling factor. So that will be the challenge. And I mean, so I'm very, very insecure if we apply this to clays. We did some of that, but like, we always write that we don't know about this.
Mhm.
Because I don't want this to be interpreted differently because the scaling factor could be very, very different. Because the surface roughness, you could have way more fine scale surface roughness for the finer media. And
Mhm.
that was not accounted for by looking at the sandy media. So that, it's a long story, but that was, something we need to be very, very careful.
Right. It's very interesting and intricate. So yeah, going back to Hoshin's point about information and information theory, information theory helps you to identify which variables are or pore scale features are actually containing more information needed to predict the transport.
What information is needed to what?
To actually inform the prediction of the transport. Do you see a potential of using information theory?
Information theory.
Yeah, for the upscaling of for this.
Yeah. So actually, this slide, right? I think Hoshin and I had several discussions of this type of multi-complexity questions. So there has to be some type of metric to determine which model can be used under what condition.
Mhm.
And so far, this type of criteria is empirical. Like we just tell you, if you have this amount of information, you can use tier three, and if you don't have profile information, then you can do tier four. So this for now we only have empirical type of guidance, but I suppose that there can be a more systematic approach to define a criteria or metric that can be used to move between the different models.
Mhm.
Basically, it's sort of the information you lose and the amount of information you have in terms of input and then the outcome accuracy. I don't know much about it, but I think it's a very general problem, right? So this is not unique for this system. We always encounter this type of options. You can have different type of models of different complexity. Then you have different level of information for input. And then you also care about different things when you apply these models for different problems. So I suppose that there can be some type of framework that can be put together to look at this. But I mean, I haven't thought too much about that. But yeah.
Okay, and my last question is about you mentioned that you already have a model for vapor phase
Vapor
PFAS.
phase, yes. Yeah.
So have you thought about extending that from the valve zone to the actual land atmosphere exchange or atmospheric transport?
Yeah, for now that we focus on the soil part, just to look at potential vapor intrusion,
Mhm.
like in buildings or like in farms. Um, when you have this type of volatile stuff, we haven't looked at like land surface interactions yet. No, but that could be an interesting aspect.
Are people actually measuring those
Vapor?
above the surface? Yeah.
Mm, as far as I know, I have not seen people publishing the measurement.
Mhm.
Actually, it'll be good for people to measure that because we don't know yet, right? So far, there's no published work that saying that in the soil pore space you have vapor PFAS.
Mhm.
This turned out to be extremely difficult to do, actually, because you have to sample the air and the concentration is super low, right? So one of the challenges of PFAS is that it's so dilute that the analytical is very, very difficult. we did molecular dynamic simulations, right? So if you have this 10 by 10 by 10 nanometer domain, you only have a couple of molecules for this type of dilute system. So, if you look at the sort of the maximum contaminant level compared to other contaminants, they are usually several order of magnitude lower in terms of the regulation. Yeah.
Okay, interesting point.
But that's a very interesting question. I don't know, and I don't have an answer for that, but I think it's gonna be an important area of research.
Yeah, my research is very tied to flux towers. So I was thinking on if you have instruments to measure methane and all these trace gases, why don't you have an instrument up there measuring PFAS or something like that?
Yeah.
Cool.
Thank you.
Thank you, Bo.
Yeah.
Maybe you could work, Leela, with Bo to figure out a way to do it. That would be very interesting.
Yep,
Yeah.
definitely.
So we've kept you a long time, Bo, but I hope you don't mind. I'll ask one meta level question. Leela sort of anticipated my question a bit. Do you have 10 minutes just to do that?
Yeah,
Is that
yeah,
okay?
of course, of course. I
Okay.
mean, it's a great discussion now.
Okay, excellent. So my meta question is about representational structures. Okay. Um, when you have data, when you have lots of data, we're now in this sort of era of machine learning. And the proponents of machine learning say, well, you got lots of data, just toss machine learning at it. It's very flexible, it learns relationships and so on. It doesn't necessarily learn causal relationships, but you can do very good predictions. Okay. All right. In the absence of data, so pre that data era, pre-computation, mental reasoning was the pathway towards being able to understand the world and the system, sort of generalization and so on. And your talk is a beautiful example of how you went through a process of mental reasoning, learning about the problem, the field, going out and seeking the information that you need, synthesizing it, putting it together, and so on. And even more than that, it reflected how much the complexity of physics, as we understand it, can enter into that structured reasoning process, somewhat structured, maybe slightly random, structured reasoning process. Yep. And for that, you rely less on data. You were able to rely on sporadic measurements. Yeah. Okay. But at least you had something to stimulate that reasoning process, the thinking process. Okay. Now we have LLMs, which have first been built by, scraping the web for human knowledge, and then been trained to do more and better reasoning, in order to emulate human reasoning processes to some sense. And then on top of that, the most recent development is agentic AI, and then frameworks of agentic AI. So not just an agent, but an agent framework, so collectives, right? And I've been recently sort of grabbed by the short hairs by this because people in hydrology are starting to think about how to use agentic AI in this context. Yeah. So my question to you to reflect as a reflection on it, you don't have to have an answer, but if you have any thoughts about it, is that the moment you go back to using agents to reason and allowing agents to access tools, human knowledge, um, does this allow us to sort of emulate the ability of human beings to work with less data? Yeah. And what can you reflect upon from your experience of having done this now for many, many years on the structure of reasoning? Sort of it's kind of, I'm asking you to meta reason about the structure of reasoning. Because if we are to build structured AI agents frameworks to do that, the human engineering has shifted to a different place. It's shifted to the place of building the reasoning structures, right? And then I can anticipate a fourth phase in which it can learn how to reason. But, presumably that's in the future. So I'm going to be working with students in 696 on this, thinking about how you would structure the reasoning process for model development. But I wonder if you could talk about that here in terms of how it appears to you, been through this process now.
Hoshin, you posed just a very, very big question, and it's a very interesting question. I actually don't have an answer to that. But I can maybe just say briefly of the things that we've gone through. I mean, you see that actually we did not know this beforehand, and we made a bunch of mistakes and incorporated wrong things, and then later found out something important. So it's actually a process of scientific quest, right? So I do think actually AI agentic, sort of this agent type. Sort of to assist discovery can be very useful because, for example, right, remember about the surface diffusion stuff. We were stuck and we did not know this was relevant, but actually exists somewhere in the literature, and it's just that we were not aware of. And I suspect that with AI could do a better job because they actually have seen all of the things in the internet, on the internet, the databases. And so that, actually, when we worked on that, that was sort of before ChatGPT was really there. But I suspect that if we did have this access to this, we might ask, what are the processes that are relevant, and we might get ideas to that might accelerate the discovery process.
Let me pin you down just a little bit because you reminded me. So you had the differential equation representation. And it took me a long time to learn this. I think you were the one who taught me this, that's based on representing forces, right? Balancing forces.
Yeah. Mm-hmm.
And when I went to school, nobody taught me this. So for a long time, it was this, what the heck are you talking about? Where did this come from? Okay. And then you have the parameterization process. And that's where your assumptions and your approximations and so on come in. But even at the level of the differential equations, you have to have conceived of what are the forces that are important.
Yeah. Mm-hmm.
Which is like saying what are the processes that are important.
Conceptual model, yeah.
Right. And then when you get to the parameterization, you have to say, can I get away with a simple parameterization? Is it linear, nonlinear? How complex is it? What factors? Right. Okay. And I think Peishi asked you about that. So my question to you is, if you had to teach this process to somebody, is there a way you would say, well, start like this and then see how far it gets you? And then these are the things you need to pay attention to improve. Do you feel like there's a structure that's emerged out of your experience with this problem where you could teach somebody and they would be able to reproduce what you went through?
So that's so I think that's I don't know. I don't know actually if I by Jasper, yeah. I don't know. I think one of the lessons, yeah, I think one of the lessons I learned through my experience of research, like, I worked on large scale problems during my PhD and then switched completely to poor scale process for my postdoc. They were actually completely two different communities. And I sort of had the intention to be exposed to both, and that turned out to be quite useful for my research. Now you can see that I was able to think in both sort of space. I do think that type of training is very useful, but then I don't know how to inject that. So in my teaching, I usually would introduce both perspectives. I would start with the poor scale always, because the poor scale is where the student actually can get a handle. It's like a poor. Okay, I can think about the poor. I can think about the interfaces. But if you look at the Richards equation and the soil water characteristics, they are all very vague and very abstract. And so I always start with a tube. For my videos on hydrology, for example, I would spend maybe a month just talking about tubes without getting into any soil and hydrology. And that turned out to be quite useful for students to understand these processes, because then they have the building blocks to then enable them to think the bigger scales.
So there's some kind of archetypal building concepts which it's useful for students to have in order to be able to understand the complexity.
That's right. So what I feel is like, whenever you introduce something abstract, if you don't have a lot of you don't have a lot of background information or like concrete information, then it's easy for the student to be lost.
Right. Your pictures where you showed the pores and I mean, to me, they're so beautiful because I think almost everybody can intuitively relate to that. Maybe not a kindergarten student, but almost everybody who has had some very basic hydrology can intuitively relate to that. And so it was very helpful in helping us understand that. Um, to me, it felt like in my own education, one of the missing components was nobody ever walked me through, here's how you go from a statement of the problem to a partial differential representation,
Yeah.
right? There's a mathematical symbolic language leap over there, which left me hanging for a long time. I think you do that in your class, right? You
Yeah, I
actually
do
help
that
them
from step by
understand.
step. Yeah.
Yeah.
So I mean, I think that's very important actually, also for my own understanding. Like that, the reason I wanted to go to Portugal for my postdoc was also because I felt unsatisfied. I'm just doing a bunch of numerics and trying to solve equations fast and robust and accurate, and which was fun mathematically. I had a lot of fun, developing numerical methods, algorithms, but I did not have a very, sort of satisfiable understanding of the processes, and so that was sort of the motivation. Yeah. So, Hoshin, I actually have to go to a different meeting, and
I'm done with my
Leila and
questions.
also Patience, thank you so much for the opportunity to present. And I have a lot of, I was a little bit scared in the beginning. I was like, oh, there are no really post media people. I might completely screw up this presentation, but the discussion was very deep, right? So I'm very happy about the interaction and the feedback.
Well, it's like I said, it's a very interesting and thoughtful group. So we invite you to come back and join us anytime. And Leela, you need to make sure Bo's on the mailing list because I think
He is already. Yes.
okay, yeah,
Sorry, I didn't ask you before, but you are now.
No, that's okay. That's okay. Yeah, we managed that. Yeah.
yeah.
Thank you.
So
I need to jump into a different meeting. Yeah. Okay. Bye.
Sounds good.
Yeah.
bye,
Bye.
guys.
Thank you.
Bye. Thanks.
Bye-bye.
Bye.
So Leela, you stop the recording maybe.
Yes, just one sec.